It's out. Oh, as you can see, okay. And this one. So I'm going to share the screen. Okay, so we're recording. Okay, we're in the second half today. Uh, go back to Colab. So we fixed the bug. I think. Did it error out or something? Oh, I had a keyboard interrupt. Okay, so, but yeah, we're going to continue. We're going to do a sign-in sheet, okay, for participation points. Pass this one. All right, so sign in, pass this around. All right, so let's go ahead and so what's your name? Sorry, Matt. Yeah, so thanks. He helped me fix the issue. Okay. But this is working now. So we were discussing the temperature to Fahrenheit conversion and doing the derivatives manually and everything for this example. So we had established the model, weight times the value in Fahrenheit plus bias to produce the temperature in Celsius. We had talked about the MSC, so that's done. And then we were doing the training loop. I have a tendency to like things written like that. That's just the preference. I write code in a way that's easy for me to pick up things. The other way, this way actually is what broke the code. So it needed to be like this for this to work. So logically, it seemed like it would have worked, but there's some technical thing with PyTorch here. Possibly it was creating a new tensor, and that was the problem, right? So yeah, go ahead. Yeah, that's what broke it. So logically, as I was saying, that should be fine, but there's some technicality thing going on. Perhaps I'm passing params as a pointer, and that was starting to break it somehow. Yeah, it's since so with Torch no grad. Okay, that makes sense. So it was yeah, so this is what's throwing it off, etc. So yeah, um, usually we would not code like this, as you guys know, but the goal is just to get into in-depth as to the update. But this fixes it. Logically, you guys understand still what's going on, so nothing has been broken. That was the only thing. All right, so if you remember, we're still today, after I finish this script, we're gonna dig deeper into loss dot backward and what it does. That's the calculus part. Thank you. Did everyone sign in, guys? Yep. All right, thank you. So that's your participation points. All right, so creating the function, training loop. All right. So it's loaded. And now it should work. So this part is just invoking that function, 100,000 iterations, a learning rate. Remember, we are passing the parameters here, requires grad equal true, which means that in the computational graph, this is the thing that we do the derivatives every time we run loss dot backward. Okay, and then params we actually don't do step, and instead we update manually ourselves. So the torch no grad is so that the system doesn't try to update automatically. And so work because we specifically want to do it ourselves. So it's almost like if I just made this params -1 for something, for some reason, or as an example, it would not learn at all. It would be pretty bad. Do you guys see that? So it's kind of like we kind of have to go out of our way to do this manually. Okay. All right. So, but anyway, that's the intuition, hopefully. Remember, this is called the update rule. It's pretty straightforward. As I've said, this is what you're adding or subtracting, and really this is giving you essentially the sign, right? Is it plus or minus? And that's it. It seems crazy that this simple rule trains everything. And you guys know that this is what's behind ChatGPT and all AI intelligence and NIO and everything is being updated in this fashion. Any questions about this? All right, so now let's go ahead. We've created the function. Remember, this is today we're discussing stochastic gradient descent. There's only one algorithm to train all of AI, and it is this idea. The idea of the derivatives was created in the 1940s. I mean, obviously derivatives existed way before, but the idea of using it for machine learning came around in the 1940s. For those of you that took ITS 365, you remember that was the perceptron. But the problem was that there was no way to backpropagate. Do you see that? So in the 1940s, they essentially came up with this idea of the derivative, but they only knew how to go from the output to the previous thing, and that's it. So they didn't know, how do I do once I get to a hidden layer 3 to go to hidden layer 2, from hidden layer 2 to go to hidden layer 1 and update everything? Because it's a neural network that's probably deeper, right? So they got stuck in the 40s at only, hey, let's take the derivatives. This is the update rule. So this was in the 40s, done, right? And our model works because, why? Because it's only one layer from inputs to outputs. Do you see that? This is almost like a perceptron type of a thing. So this works no problem. And I forget the name of the people that did this. I wish I remember. I don't remember right now. But they came up with this in the 40s and the perceptron. The innovation, but that's as far as they got. In the 80s, Geoffrey Hinton, whom you may have heard of him, and his team solved the problem of going to previous layers. And therefore, that's why the algorithm is called backpropagation, because it is essentially that fact, right? That they could go back and train other layers, not just like still using that calculus derivatives approach. There's only one technique for doing this. There may be variants, derivatives of it, derivations of it, but there's only one algorithm for all of AI. And it's this one. This is why Geoffrey Hinton is considered one of the most important people in artificial intelligence, right? He invented the thing that does this. Okay? Anyway, so we've done this part. So now we should be able to train. I'm going to go ahead and run. What? Where? Oh, yeah, params. Somehow I lost that. Thank you. Good catch. Wow, you should be teaching this class today. All right. So yeah, so training loop has been added, and now I'm going to go ahead and run it. And there we go. It's now training. The loss function has gone down from 1763 to 25. You can see it's going down. So essentially, it is updating. We know that our loss values need to go down, and we know that these are the parameters, our W and our B. Do you guys understand how this works? And the only thing so I've done the update part today. In the next Jupyter, we're gonna dive in a little bit into this one, params.grad. But let's finish up this script so you can see it finished, it seems. Okay, we got a green check here. So it has finished. The loss did go down, which is good. All right. So now And this, I always like to do this almost as a segue to transfer learning, because this gives you, in the most simplified way, the idea of transfer learning, which, like I said, is the topic of ITS 530, the next course in the sequence, next semester. So here we can, guess what? Print result. What's result? The weights and the biases. This is the thing of value. This is the thing that everyone wants. If you have a company that builds AI, right, this is your IP right there that you want, because that solves a problem. Let's say your NIO project solves something, right? You're getting that input, right? So that's essentially the thing that you figured out. Also, as I said, if this was DeepSeek or something else, this would be 671 billion of these. These are called the parameters. This is essentially the intelligence. If you were doing transfer learning, let's say that you train this model and you are going to use it, right? So what do you need to do? You just essentially take, the architecture because you'll agree on it. So you just build this architecture exactly like that, and then wait for his email or whatever to provide you with these parameters. And you have essentially done transfer learning. And then from there, you can take that model now, maybe that costs millions of dollars to do, and proceed to fine tune it. And fine tuning does not require the massive amount of data that pre-training requires. That's the idea. All right, so now let's go ahead and try out our model. So our model is going to take some temperature plus the result. We're going to pass it where result has the two parameters, W and B. So we pass it exactly as it expects, and it's going to tell us what that temperature is. So, all right. So we did that one. And now we can go ahead and just print it and see how close it got. All right, so my temp is 33 degrees. So 99, almost 100 Celsius. No, sorry. 90, we're converting. Yeah, we have it here. So what are we converting? Model takes Fahrenheit and produces Celsius, right? Fahrenheit. So Fahrenheit is okay, so that's what it is. That's that I don't know that value. So what's a Fahrenheit value? 32 should be 0. Yeah. 32 was 1. So 32 Fahrenheit is a freezing point, which is close to 0. If we want the boiling point, 212, right? So 212 should give us about, okay, 88. So maybe we were missing some data on the high side, if you guys remember in the original data set. So this is data driven, and so we don't have that much information. Does this make sense, guys? That's it. All right, so that's this example. So you have seen the process of updating the weights individually. You get this idea of the weights and transferring them from one architecture to another. That's essentially the simplest case of transfer learning. All right, so now that concludes this part. Now we're gonna move on to focusing in the next example. We're gonna focus on this part, loss dot backward, and what's happening there. And we're gonna play around with it a little bit. For those of you that have taken calculus, essentially you're familiar with derivatives, you have a function, and then you take the derivative of it and you get another function. But in PyTorch, it doesn't work like that. In PyTorch, you have a function and you take the derivative of it and you don't get another function. Instead, you see it in the data itself. Like the function is there, but you don't actually get the, intuitively we would expect, okay, x2, so I should get 2x as the derivative, but you don't see the derivative, which is strange if you've done math. What you see is the value. Okay, if I plug the value in the original function, I get this result. And if I plug the value in the derivative of it, I get this other result. Those are correct in the same way that this equation you derive it to become this equation. Okay, so you see the values. So we'll see that in our next example. All right, so I'm going to switch over now because we've concluded this example, and I'm going to focus now on the mechanism of just loss backward. And I'm going to elaborate a little bit on how that works, and that will wrap up this deep dive into the inner workings of PyTorch. This is really important, as this is why we need, by the way, PyTorch. If we didn't need this stuff, we could just use NumPy, right? All the tensor operations that we've done all semester, it's perfectly fine in PyTorch, sorry, in NumPy. But here, this is the heavy lifting of PyTorch. So let me close this Jupyter Notebook. Let's go back to Brightspace, table of contents. And so now, so essentially, let's see where we are. We've covered your first neural networks, cross entropy, NIO, performance metrics, CNNs, and now we're just wrapping up these two modules here. So we're going to go to our code section. Okay. We've completed this one, I believe. This was Scratch. Yeah, the Celsius and Fahrenheit. Now we're going to dig deeper into Scratch gradient losses. So this is essentially diving a little bit deeper into how the autograd mechanism and how important this is and how it relates to derivatives and so on. Okay. Remember, what are we getting? Doing all this gives us, because we just saw the update rule, plus or minus. Make sense? All right. So let's go ahead and let me plug in a machine. So let me open Colab. Okay, let's open a. And this one also will not require data because we're just really doing some functions and taking out derivatives and things like that. Power cord. Okay, so yeah, so let's start at the beginning. We're gonna need some libraries here. Okay, so we're gonna use Torch, NumPy, Matplotlib, just like before. Then we are going to just play with some values. So let's bring in X. So we're going to be using X as the value here. And we need to define if it requires grad or not. So we need to decide if that is going to be set to true or false. But here, let's just create a constant value, 14.5. It's a torch tensor, and we print it out. There we are. Then that's going to be the parameters, right? So remember, it's always going to be some value that goes in, and then we need functions. Okay, so let's take a look at a function here. So this is some function, which would represent the neural network. I'm not going to be using exactly the usual W times X plus B. You understand that any other function would be similar to that. Right? So here I'm just using X plus 5. So obviously I'm going to bring in 14.5 in here times 5, right? And that's going to be 19.5. Do you guys see that? So this is the equivalent of the function without having a derivative for it, okay? But then we can take the derivative of this function, right, or some other function, and then now when we run a value through it, it's going to be different. And that's the key. What is that value? That's the value that we're searching for, okay? So here we are. Automatic gradients, as you know, now we're using the autograd mechanism. So I'm going to grab this one. And now I'm using X, but it's 3.5, but I'm setting that the value requires grad. Okay? So now whenever I, do the backward mechanism, it'll take the derivative of the function with respect to this variable. And so that's essentially the idea. So now we have X, still 3.5, but it requires grad. So in the computational graph, we can take the derivative of it. All right, let's keep going. So now here we have a function. Okay, here's a function. All right, some function. This is y equal x minus 1 times x minus 2 times x minus 3, right? If this function currently, we haven't taken the derivative of it in terms of x, right? So this, if we run 3.5 through it, it's going to be 3.5 minus 1 times 3.5 minus 2 times 3.5 minus 3, right? And that's the value that we get. Any questions on that? All right. So that's essentially a normal function. The idea of the derivative is we can take the derivative of this function, and then when we run x through it again, now we have valuable information. That's essentially the mechanism. All right, so I ran this. It gave me 187, I think. Yeah, 187.5. Okay, I can also write this as a function. This is just a demo that we can put the equation in a function, very similar to what I did in the previous script, right? And so x goes in and produces y. All right. So let's plot this one just to get a feel for it. We know it's a function, okay? Just to kind of give this idea of a graphic, since we're going to be referring to things. So here we just have the x values, right? So iterate from -1 to 6 and produce the values in a list comprehension. We convert that Python list into a torch tensor. We can print it out, and then we run x1 through the previous function to get the equivalent value for each x input. We have a y input, right? Those are our x2s. And then once that's done, we're just going to plot the function x1 and x2 so that we can visualize. And you can see there it is. That's our function, right? So the key idea is now to take the derivatives of, at key positions in the function. This is what you always get intuitively, right? So what is the value here? Is it sloping? So for instance, here, it's like not sloping down, right? Right? But here, yeah. So here you could potentially get stuck here, for instance, if you thought about it. Or, here we're constantly want to be going down. So that's the symbol that we want to get. So let's go ahead and try that. So best thing is that we can see it. Okay. So let's look at this example now. Change the number to 3.5 or just re-establish it. So 3.5 does require grad. We print the value. It is 3.5. We have our function over here. which is going to be this one. X minus 1 times X minus 2 times X minus 3. So you really have to work this out, multiply these to get the actual function, and then take the derivative of it. So here I run, the value is still no derivative, but this is in the computational graph, right? You guys realize that as I'm doing this in Torch, I'm adding this to like this tape, right? That's the computational graph. And then I can just reference everything through Y. Like I grab Y, right? And I'm basically touching on all these parameters. So now I'm just going to go ahead. As you can see, the value was still 1.875. Okay. Now the notation, the math notation is that you take the derivative of Y in terms of X. Okay. In this example, we only have one variable, X. But in a neural network, you'll have multiple weights, right? So you have to take the derivative of that function with respect to each of those variables. And in another example, we'll see that a little bit. But in this example, let's just think of one value. So here's the magic. Backward, right? This this 2 lines of code that have been doing all the heavy lifting for us. This is the autograd mechanism of PyTorch. And now this function y, which is tied to all these parameters, is what we say y dot backward. Okay, in the computational graph. And because x requires grad, it's going to take the derivatives for those. Okay. So now we don't get the resulting equation, right? But when we run this, you'll see in a second that what happens is the value is going to store the derivative. So this function, the previous function, this one, if we took the derivative of it, the derivative of y should look something like this. 3x squared minus 2x plus 11. Do you guys see that? So if we run, x is the thing that we took the derivative of, right? So if we printed x dot grad, not x, but x dot grad. You guys see the difference? So xx is still whatever, 3.5. But with respect to this equation, the value is now 5.75. So how do we calculate that? Is we run the original x through now the derivative of the original function to get the value 5.75. So this thing here is the original equation. This is the derivative, right? You guys agree. I literally said y is equal to this, correct? Yeah. So I said y is equal to that. So that's the original equation. That should not be a mystery, right? It's hard-coded. I took backward of y. Okay, great. What does the equation look like now? That's something that if you've taken calculus, you would know because you did it by hand, but in PyTorch, that it doesn't give you that. However, I have added this here just for convenience, right? So that you can understand that. It's like it gave us back this one over here. So now what you can do is plug in the value through it to corroborate, right? So we say that x dot grad would be the result of running x through this one. That's your 5.75. How do we prove that? Well, let's take the original value of x, which was 3.5, and run it through this equation. Do we get 5.75? Let's try it. So this would be 3.5 times 3.5. And we can actually, because I've coded it. So 3, right? So 3 is 3. x2 is just going to be x times x minus 12 times x. There it is, plus 11. Plus 11. All right, you guys get that? So now let's run that. So 3.5 is the value that we would plug in. The original x is 3.5. But instead of going through the original equation, which is this one, to provide 1875, it goes through the derivative of that equation, which is this one. And so if we run it, 575, guess what? It matches what is already in x.grad. Do you see how it works? It's a little strange, as I said, especially for anyone that has taken a calculus class, because we're so used to getting the function, but we really just need the value, right? So this is the value that tells us, so this came out positive. So that's going to be what? In the update rule, params minus 0.0003 times 5.75. Do you guys see any question? Do you have a question, comment? Yeah. So yeah, do you guys see how it works? Yeah. So anyway, so that's the example of getting the gradients. So notice that the key thing is 575 matches to this 575. Another lovely example, right? So more involved in calculus here. So this is let's do another example just to drive this. So here there's two functions. The main function is, this actually represents, right? Like a couple of layers, something like that. So we have z equal 2y plus 3. And then we have y equal x2. So calculus says, okay, this is the easiest example in derivatives. X2 is 2x. Like, that's, you know that by heart. And so, but you derive things in terms of the other terms. So in this case, we would, because of the way that this is done like this, we would do derivative of c in terms of x, which is what we need, which is broken out into the derivative of c in terms of y, because this is actually written in terms of y, times the derivative of y in terms of x. Do you guys see that? So this is just how the math works. Don't worry about it. And then we need each individual one. So the derivative of c in terms of, and I think I have an error there. So it should be, no, the derivative of z in terms, fine, right? So 2y. So the derivative of c in terms of y is 2y. What's that? Yeah, give me a sec here. Yes. Oh, right. So this is the same thing. Sorry about that. All right. So this is 2 times 2, 4x. Yeah. So derivative of c in terms of x. So that's the whole thing. 2, and then, right. So this is the way that it's broken out. The derivative of c in terms of y will be 2. So that's this 2 over here. And then the derivative of y in terms of x is going to be 2x. So that's this 2x over here. And then these 2 is 2 times 2x, which is 4x. Yeah. All right. So anyway, so this is how the math works out so that you figure out the value. So now let's try it out in PyTorch. So I'm going to copy this one over here. Okay, so again, we have x. 3.5 requires grad equal true. So we print it out. Okay. And then we're going to write out the equations, the exact same equations. Okay, so y equal x squared and c 2y plus 3. So there we are. So we have those values there. Okay. Now we take c dot backward. So we're taking the derivatives, right? And we've defined that we want x to require grad, right? So that's also has been established. So c dot backward. Okay. So now x is 14. Do you guys see that? And that's so again, we have x through the function gives us a value. X through the function after the derivative gives us another value. And that value should be 14. To corroborate, well, we know that over here, right? We know that the derivative of this is this one over here, right? So manually 4x. So we just corroborate this. X is 3.5, I think. So that gives us 14, and this 14 matches. Do you guys understand? So essentially, the autograd is giving you the value. It's calculating inside, although we don't see it, that the derivative of z, the derivative of c for this one in terms of x was equal to this, which was the derivative of c in terms of y, 2, the derivative of y in terms of x, which is 2x, and so the answer is 4x, okay? And so 4 times x also gives us 14 for that value. And again, this is the value that we would use for the result. Any questions, guys? Anything making sense? So that's the idea. And so that's how we obtain the values that we wanted. Okay, so essentially, how does all this relate to training? From the previous example, you assume the output is z and assume the correct value is t, right? So we're taking the difference, squaring it, right? And e becomes the node that we're holding. That's the function. So we start taking the derivatives of e in terms of the respective weights. Do you guys see that? So just like what I was doing before, here we're going to have y minus the real squared. That error, we take the derivative of it in terms of the individual weights. The individual weights are going to be the parameters in z, essentially, like the example that we just did. Any questions? Nope. All right, so that's differentiation. Let's take a look at a few more things here. So we covered this one. We covered that one. Yeah, I think that's almost all of them. I think the only other example I had was batch normalization. So essentially is something like when you have a batch of values, when you're doing the training, you had one when we're using between layers something like dropout, we had batch normalization. So the idea is simply that you take the mean of it, for instance, or you normalize the data. And that so it's something like this. To go from a batch of data to just one specific value. Okay, and that's kind of what's happening with the normalization. But anyway, so that's I think that's all the examples that I had for today. So now what I'm going to do is I have a set of slides, right? And I'm just going to wrap up everything related to this topic of sort of neural networks optimization, and that's essentially it. So let's go over here. Let's go to the table of contents. So we have concluded this topic here, losses, batch normalization, differentiation, and gradients. Are there any questions on this idea? Right? So we talked about today, we trained a model, we looked at how we had an update rule, we looked at that, and then we know that the backward function, we just calculate that requires grad. So actually, let's link it back, right? So if we go, just to tie them together. So in this one, scratch optimization, the update rule was here, right? Learning rate and then params.grad is the value from the derivative. That's what I was getting here, x.grad. So if you see x.grad, params.grad, that's the value that we get. That allows us to do the update. And that's entirely, exactly how it works. Any questions? All right, so if there's no questions, then let's consider this topic covered. And now let's go to okay, so this module is done. And now let's go to loss functions, this module over here, which is just a set of slides that I have that we can use this to wrap up. So I'm going to use the whiteboard for this one. So I'm going to switch over to the whiteboard. Okay, here we are. All right, so this is kind of just wrapping up with a few notes for this idea. So let's start with the fact that we have two functions, right? So we have, what are the functions in neural networks? We have the inference function, and then we have the loss function, correct? So today we had a perfect example of this, the Celsius to Fahrenheit converter. So the inference function was y equal w times x plus b, right? So that's the function that we saw. And then the other one, we used MSE, which was y hat, and let's call this one y hat actually, minus y squared, right? And then usually like a sum to calculate a mean, something like that. But this is essentially the two functions that we have available for training. And we did that today in PyTorch. This is usually the neural network. So this is the architecture of the NN, which can get more complex. Okay. And of course, other loss functions will use cross entropy. Now, the losses are usually denoted by the term J. Okay, so it's going to be either MSE for regression or cross entropy for classification. There's going to be other ones that are going to be there, but essentially they're kind of variants of this one. Okay, so let's look at the idea of the inference function first. We have the inference function. So we're going to have linear regression. Okay, and that's going to be where we have a neural network, perhaps that like a very linear one that has just one output. Okay, and the range for this one is going to be somewhere minus infinity to plus infinity, right? Now, on the other end, we're going to have the classification problem. So this could be classification, logistic regression, one of those. Classification, okay. So such as logistic regression, the simplest case. Logistic regression. So what is the difference between this one? Essentially that we have a neural network like this. We could have a neuron like this. But here we have a function, right, that is going to map it to be in some range, let's say between 0 and 1. Okay, something like that. Or we could have two neurons as well. All right, so this is now graphically, the regression is trying to fit. If we have data like this, right, we have data like this. And here also, we have data like this. The functions have two different goals, right? In the regression, we're trying to find weights that follow that behavior, correct? Produce a line that fits the data. In logistic regression, we are still playing with the W's and the biases, but like that, assuming that we need to have points that are different. So these are green now. So you can see we're trying to separate between two sets of points. So that's the goal in this one. But the mechanism is the same, as you guys have seen. It's just that the goal that we're trying to accomplish is different. Does that make sense? So the line just flips differently. All right, so that summarizes that. Now let's look at the loss function. So this was inference, right? So now let's take a look at loss. As I said also, whoops, working. Oh, sorry, I must have touched this. Okay, so loss here, denoted by J. So this also, it's important that you guys are aware that this also has a graph, a graphical representation, but it's based on another function. So in the previous one, the graphical representation is like this one, is one chart. The loss function will have its own corresponding chart. So let's take a look. So linear regression, once again, simplest case. And the J, as we just did today in the temperatures, is going to be 1 divided by N y hat minus y squared. Okay? Anyone know what this function looks like? If we call it J, what's the shape of that function? Seems crazy. And remember that what is J, by the way? Well, J is nothing more than the inference function. So W times X plus B, correct? So whatever J is, it's in terms of W and B. Do you guys see that? What is the shape of that equation? What is the shape graphically of this function? Well, if we look at it, actually, y hat minus y squared, once we take that difference, which is called the error, becomes e squared. If I just make it more familiar to you guys, x squared. Do you see that? What is x squared? It's got a bowl shape, right? So for instance, let's say that, it's going to look like that, essentially. Right? So this type of shape. So that's all right with that. So usually this is called a quadratic equation, okay? And it's essentially the graphical representation that we can think of in the simplest case of MSE, right? Now, it's referred to as a bowl equation. So intuitively, what's going on over here because it's in terms of a loss, the loss is trying to be minimized, right, to a certain point. And so on this axis is called cost, okay? And then here, this is going to be in terms of y, right? But really, y can be expressed in terms of the parameters. So we can think of it as the w, okay? So let's consider an example here. If we are here, right, what do? The loss function, right, this loss function, we would take, as we were doing just before, we were taking derivatives of this function, j, in terms, which is also the error, technically, in terms of these parameters, the w's and the biases. Do you guys see that? So graphically, that translates into saying, okay, we are at this point in the equation in terms of the loss, right? We haven't optimized it yet. How do we update that weight? So we can say, okay, this is W1. At that point in time, we take the derivative of this function in terms of y, which means in terms of w or b, in this case, w. What does this tell us? It tells us the slope of the graph, right? Which is essentially that dot grad. So that tells us what? The direction that we should go. So the symbol might be here. It's a plus. So how does that translate? So that means W1 plus the learning rate, LR. And so we take a step in that direction so that we are going down slope to find the optimal solution. If we are on this other end, right, for whatever reason, okay, what does that mean, right? Minus, right? Exactly. So again, remember, this is the cost function, MSE. It's called a quadratic equation, E squared, right? Because we're taking an error. So, right? So we are essentially, this equation has this representation in the space of this equation. But y is actually in terms of w and b, which is the parameter that we're trying to figure out. So we can say, okay, we're taking the derivative of j with, with respect to w at this point in time, because we're in whatever iteration we are currently at. So this is w2. When we take the derivative of this, as we did, w dot grad, right, it gives us this slope, right? And this slope translates into something like being negative. Do you see that? And so now we know, just go, minus, right? That's the value that it gives us. So now our step is just going to be that, which is W2 minus LR. Do you guys understand? So the thing that we were doing mechanically with the equation, you sometimes see it explained in this way, and this is the connection that you have. Any questions, guys? Yeah, good. Well, it's because you can see it in the direction, right? So what gets you lower? Look at the direction of the step. If this scale represents weight in this example, right? How do we approach the bottom? We want to get here. When we take the derivative of this function j at this point W3, right? It's going to achieve the lowest cost possible, whatever it is. So at that point, the symbol, that derivative is, the tangent is 0. So it's equivalent to plus 0. That's mechanically what is happening. So the weight does not update. It stays at that parameter because that's already the optimal parameter. But if it's here, it gives you either this slope or the other slope. That's my drawing may not be great, but if maybe like that, it's that slope or that slope. That's just calculus does that. And so it's telling you which direction to go in. You're going in. It could be, for instance, that this one is negative, but then this one is going to be positive. That really doesn't matter because it's going to be the opposite. That's right. The goal is to get close to W3. Yeah, the loss is the lowest. Yeah, exactly right. So this function is the J that, in our code, we always call this loss. So that's that loss that we're printing that is going down until it's like very close to zero, because that's really what we're trying to do. The beauty of this is that this equation helps us to get to that. It like achieves that goal perfectly. Yeah, go ahead. Yep, exactly. And this is exactly how it works. Like when you took your calculus class, they probably explained that in graphical terms. Obviously figures don't really exist in computers, right? Only the data exists in the equation. But essentially what it's giving you, which is what I showed you in the previous example, that x dot grad or whatever it was really giving you, honestly, this plus or that minus, and that's it. And then we would use that term times the LR to determine if we were going to add or subtract from it. And this is just graphically showing us the same thing. Yeah. Yeah. Any other questions? Yes, please. Sure. Okay. I see what you're saying. Yeah. Well, I mean, this is like how the calculus part works, but why does that happen? Why does the loss go up? My answer in terms of this is that what's happening is it found maybe a value here, and then it just starts going back up, or it just starts, not arriving at the optimal thing, because also it's not just for a neural network, it's not just going to be this simple. This is the example of just this guy over here, right? But now when you have tons of weights and everything, there's a balance that's happening. I will actually kind of conclude with this today, with this idea. All right. It's going to be like a count. So think of it, if this is just one, right? One weight that's like, and using MSE, then now if we had another weight and another weight, and you have to start finding a balance, so it becomes like a more massive space of things going on. You see that? But yeah. But anyway, this is the mechanism of stochastic gradient descent, and hopefully it makes sense to you guys. If you've ever heard an example graphically of a derivative, you have a function, you take the derivative at that point is a tangent to it, right? The tangent translates into either plus or minus, and that plus or minus translates into what you need to do in the update at that point in the loss. Remember, you're doing the loss incorporates, it's the function that represents this one, whereas this one here is only this graph. There's two graphs involved, okay? And they're not the same space. This is the space of the inference function, the line and this is the space of the loss function, a different one. Related, but a different one. Okay? So let's move on to a new one. So I can say then that for regression and for classification, we have two graphs each, right? For the data, we have the line that fits it. Yeah. Regression we know uses MSE, so it looks something like that for the simplest case. For classification, but we have this notion that it's a class problem. So then the line that separates it is like that. And what is the now what is the graph for the loss? So we already talked about the losses. This one we said was MSE. Do you guys remember that? So what did we say for this one? We said it was cross entropy. Correct? And we already talked about cross entropy. Remember, there were two cases when what we wanted was 0 or what we wanted was 1. So essentially, if we want to put them together, we could do something like that because we know that one or the other disappears, right? And then this is still the cost over here for MSE and for cross entropy. And so, but the idea intuitively is still the same. If we are here, for that point, we take the derivative of it, right? At that point in time, this might be negative, and so given that this is W2 minus LR. Do you guys see that? Just like the example we did. If we are over here, and the goal is different, right? So, we have a goal of being 0 or 1, then one or the other goes away, right? And so at this point, we take the derivative. This might be positive because we're taking a step in the opposite direction. Okay, so that becomes W1 plus, because it's minus plus LR. And that is the update rule. And that's essentially mechanically how it works. And that's why they're called gradient descent, essentially. Do you guys understand? So we explained this already with the cross entropy and the two functions in that lecture. So I've talked about this. So just kind of to remind you with cross entropy, the equation was we wanted to either predict 0 or 1, the real class. In the binary case, so y equal 1 versus y equal 0. So that the cost function, whereas MSE is this one, as we did today, the cross entropy, and this is binary entropy. If we put it all together as one equation, it is log of g, which is some function, w x plus b plus 1 minus y log 1 minus the function g of w times, w times x plus b. So if you notice, I'm plugging in here the inference function, right? So this is what could be y hat, for instance. Okay? But I'm plugging, so another way of writing this would be y log of y hat plus 1 minus y log 1 minus y hat. Do you guys see that? So essentially, y and the real and the predicted, very much like over here, I'm doing, I'm doing real and the predicted. That's essentially as here, but you can write out y is really this equation, w plus x, w times x plus b. And remember, the key thing is if this one is 1, then this is 1 minus 1, which is 0. So this term goes away and we're only left with the other. So that's why graphically the losses would be like this, where one or the other is canceled out. All right. Any questions on that, guys? All right. So that is the cross entropy. So we've discussed that one. So I'll leave that for you guys to go back to. Okay. So that should be that. So I completed one of the slides. I'll do the other slide. Okay, so in this slide, I'm just going to summarize architecture. So I'm going to look at that. Okay, so let's take a look at, we're going to look at several inference functions and kind of put in all the terms. So we have, for instance, the perceptron. Okay. We have linear regression. We have logistic regression, which is a classification. Which is a classification. We have an MLP, which is a multi-layer perceptron. And then we're going to have deep learning, just going to denote it as DL. So this is just obviously about inference functions, okay? So the perceptron was simply the first neural network in the 40s. It looks something like Z equal W times X plus B, okay? And it had a strange, not a strange, but a simple step, a simple function F that took C and made a choice. They called a step function, okay? So that was the original thing. Then a simpler, and it had the optimization was just a simple update rule. Simple update, which is really interesting, like elegant, but it's a simple equation almost like a fixed one. Then we have the linear regression, which is y equal w times x plus b. And we know that it goes from minus infinity to plus infinity. The optimization, for instance, something like MSE, all right, least squared error, etc. Then we have logistic regression, okay, and that's going to be z w times x plus b, and c goes into another function, f, to produce the y, but this is more, and this is trained over cross entropy. Cross entropy, okay, for the classification problem. Then we have the multi-layer perceptron, so that's going to be Z1, which is equal to W1 times X plus B, okay? That goes into a function, ReLU, etc., Z1, to produce H1, right? A hidden layer, if you remember. And then that hidden layer goes into W2, H1 plus, this should be 1, plus B2 to produce Z2, and then that C2 goes into another function to produce the final Y. Do you guys see that? So that you can see how you're building from the original ideas, but a lot of it is pretty much the same. For the MLP is also cross entropy in the classification. And now if we do deep learning, it's essentially the exact same thing, but scaled up even further. So that's going to be C1 W1 times X plus B1. Then this C1 goes into F. That's C1 to produce H1. Then it's going to be W2 times H1 plus B2 to produce Z2. And, then that becomes, goes into an F, C2 to produce H2. And this is just ... from it, right? So that's just until the final example or the final layer, which would be Wn times, what is it? Hn minus 1 plus Bn, and that gives you Zn, which goes into a function Cn to produce the final output Y, and this will be another cross entropy. So you can see the structure, how it is. That's essentially an inference functions. That's the scaling of it. Okay, and we can just keep going like that forever. We've talked about the architectures already, so you guys are familiar with that. I'll talk a little bit about activation functions, just summarize that. We've seen a lot of them, but let's kind of summarize activation functions. Activation functions. So we've got something called a step function. That's imagine it's C goes in. So what does it look like? It's going to be like this. Like that. So it's either 0 or 1 in this scale. So it either produces a 0 or a 1. Okay, if it's negative, 0, otherwise 1. We've talked about the sigmoid. Used it quite a bit. Sigmoid Z. In this chart, the value goes. What does it look like, the sigmoid? Like an S, right? From 0 to 1. Like that. Do you see that? And we've also used this one. So not as sharp as the step, right? This one is more a bit smoother. The tan H is pretty similar, but just in a different set of values. So tan H of Z is going to look like, change to blue. Same thing, but from -1 to +1, so something like that. So -1 +1. You see that? So you've seen how these functions are really valuable, right? We did ReLU for some trick, right? Remember what a nice trick the softbox loss function is, right? So these functions can be very helpful if you use them cleverly. ReLU. And there are others like JELU. I'll skip that one, but ReLU is a very popular one. The rectified linear unit, also known as the hockey stick type of function. So this one goes from like that to like that, right? So essentially, the range is from 0 to plus infinity. No negative values. There's one called the leaky ReLU, which I think you guys saw me use in one of the last examples that we did. So the leaky ReLU essentially it's called leaky because it lets a little bit of the negative leak out for whatever reason, right? So it's going to be something like, and then like that. So it's got a little bit of a negative component, but very small. Okay? Does that make sense, guys? And there's many others. There's GELU, which I will skip, and people are constantly inventing new ones. GELU stands for Gaussian linear unit. So it's got a little bit of a Gaussian function in it. Okay, we talked about optimization quite a bit already, I think. I believe you guys understand this. Oh yeah, I have one last slide. So there's one more thing, couple more things I'll do, and then we'll be done with this topic. So one, I did this for cross entropy, but I will do it again for MSE just in case this is not obvious, right? So for MSE, mean squared error, we know the function J is equal to the sum of y minus y hat squared, okay? So remember that y hat is the inference function. Y hat is wx plus b, right? That function. So essentially J is really y minus wx plus b squared. Do you see that? So it's actually incorporated there. Remember that this value is just a real value, and that's why we don't take the derivative of j in terms of y hat, right? We take the derivative of j in terms of these parameters, the w and the b. So essentially, in the loss function, when we do this, right, this equation captures the quadratic equation, but we take it in terms of these values, the actual w's at this point in time. So that's why we map to w, because that's really the determining factor, okay? So that this value is decreased. Does that make sense, guys? So this, we plug in that one instead of y hat, which of course comes from being the inference function itself. Yeah, all right. So these are just some of the ideas. Now, any questions about this? This is just getting into the math aspects of how it works. All right, but feel free to ask questions if you have them. The last thing I will show you is, as I said, we're not really looking at just one parameter, right? We're actually looking at a landscape of parameters that have symmetry. What that means is the following. So it's more complicated than that, but let's think of it this way. Now that you guys understand that these graphs represent the loss function, right? So not only do we have multiple parameters like curves, right? But also there's symmetry. What that means is, think of this neural network. Okay? If I get a set of parameters, like a combination of weights, let's imagine that these weights are all threes, just to keep it simple, and these are all fours, and that makes it a great model, right? But also there's symmetry in the sense that I could find another neural network where actually the parameters are 4 over here and they're 3 over here. And that one is still also great. Do you see that? So there's two solutions, correct? How you see how there's two solutions? So essentially then I just like duplicated the landscape. And so that's why optimizing is really a complex problem of wherever you are, minimize it as much as you can. But you're not always, like if I'm here, I can go in this direction, I find an optimal solution, or also I'm like here and I find an optimal solution. So wherever you fall, you just go down until you find the lowest possible. But there were other possibilities. That this arriving here just means that you ended up with that architecture, which solved your problem really well. If you had fallen here and ended up here, then you ended up with that architecture, that solution to your model, that set of weights, but there were optimal solutions. So a simplified way of looking at this is that the cost function J will look as, and remember that I'm drawing this in 2 dimensions. This would likely be in higher dimensions than that. But this is just for intuitive purposes. Okay, we've already talked about how this is in terms of, J is, keep it simple, y minus y hat, right? Take the error of that. We know that y is really in terms of w x plus b. So we're talking about the w's here. So when we start this creates the function. This creates this landscape essentially. Our goal is to take the derivative in this landscape and arrive at the bottom. Okay? But what happens, so that's why we want to initialize our values randomly, right? So the intuition here is almost like if this is a mountain range, imagine you're an airplane flying overhead and you're dumping paratroopers. That's the weights, right? So where are they going to fall? If they fall here, let's say that you fall here in your random initialization because it's the W's, right? And you randomly initialize them. So they initialize to here. At this point, what do? Stochastic gradient descent. Guess what? You get stuck there and you cannot get out. Unless you took really large steps, right? Then maybe you get out of there. But where are you going to end up? So what happens, this is a serious problem, not a serious problem, it's a highly studied problem, right? The optimization landscape. They study this. This is, So anyway, this is called a local minimum or local minima, okay? So the term is local minima. We're really getting into like optimization theory here. It's a solution. Do you agree that the weight here is better than the weight here, correct? That intuitively tells you, yeah, the loss went down. So obviously this model is good, but is it the best possible? No, right? ChatGPT. Let's say that all this time, since 2017, people have been training ChatGPT and it's getting stuck here. We're obviously leaving performance on the table because we don't quite know. We're just kind of randomly. Maybe we get lucky and we start here at this W. If we do stochastic gradient descent, it takes us here. Would you agree that this is a lower local minimum? Yes. What does that provides better answers, essentially translating into ChatGPT probably being smarter, right? But did we leave money on the table? Yes. We never found that solution. What is that solution called theoretically? The global minimum. So this is a quite studied problem in machine learning. Stochastic gradient descent is more of a iterative, right, process. Not a so it has an empirical solution, but it doesn't have like a precise solution. It's an optimization, but there is no like, oh, automatically I can arrive at that one. We have to search for it. So that's why trying different randomizations in the beginning, that's why trying multiple starts and taking the average of all 10 or 100 is useful. Do you see that? This is why people are constantly doing all these things, because they're trying to find a better solution. Hopefully, they start a weight over here, and then there you go. It arrived at the global minimum. So theoretically, this has been studied highly. Some people argue this is not that important. They're not that big, the differences. That's possibly true. Or some other people say, well, just going a little bit further down might be a huge improvement. Do you guys understand this idea? So this is exactly how stochastic gradient descent works. You know, we've talked about the functions. It creates more something like this in higher dimensions, but it's still the same idea of going down, essentially, through the mechanism. Remember, it doesn't actually create a graphical thing. It's all done through the math, essentially, as I demonstrated with the x.grad. All right. Are there any questions, guys? That's essentially it. We're done with this. So I will end this this video here. We have one more lecture next week, which will just cover stable diffusion, just going over that algorithm, but it's just looking at the algorithm. GANs also a little bit in the 2 sessions that we have. That's the end of it. All right, so I will end the video here.